everyone. I Pritha Gupta welcome you all to the Swayam online course on basic principles of energy management and energy audit. In this course, I will be dealing with the topic renewable energy sources. In the last lecture, you all have got the basic overview of the various types of renewable energy sources that are available. Now coming to today's lecture, in this we are going to learn about the very first renewable energy source, that is solar energy. The most precise definition of the solar energy is energy from the sun. Basically, solar energy refers to the radiant energy emitted by the sun in the form of electromagnetic waves or radiations, primarily in the form of visible light and heat. This energy can be harnessed and converted into a usable forms of power such as electricity or heat using various technologies and methods. There are two main forms or types by which you can say we use solar energy is number 1, thermal energy. A solar collector is used to transform the solar radiation into heat energy. This thermal energy can be used directly to warm water or for room heating or for generation of electricity by turbines. Second, electric energy. The solar radiation energy is directly transformed into electricity through solar cells. Sun, the source of solar energy, is a huge glowing sphere of hot gas with 1.4 million kilometer diameter. Most of this gas is hydrogen about 70% and helium about 28%. Due to nuclear fusion reaction of hydrogen with helium, internal temperatures reach over 20 million Kelvin. The resulting loss of mass due to fusion is converted into about 3.8 into 10 to the power of 20 megawatt of electromagnetic energy power that radiates outward from the surface into space. The sun radiates in all directions and a small part of the radiation reaches the earth. When designing and sizing a solar energy system, reliable solar data is required. The most relevant data is the average daily radiation, that is the total solar energy received per day per meter square on a horizontal surface. Global radiation consists of the direct sun radiation and diffuse radiation of the sky. The strength of the radiation of the sun depends highly on the location of the earth and is directly dependent on the hour of the day. The global radiation or the total radiation is a sum of three components, namely direct radiation, diffuse radiation and reflected radiation. Each type of radiation is characterized by its direction and behavior upon reaching the surface. Number 1, direct radiation or direct solar radiation. Direct radiation refers to sunlight that travels in a straight line from the sun to a specific point on Earth's surface without being scattered or absorbed by the atmosphere. It is also known as beam radiation or direct solar radiation. Direct radiation is highly concentrated and provides the most significant portion of the solar energy at the surface. It is responsible for casting distinct and sharp shadows. Direct radiation can be measured using devices like pyranometers, which capture the intensity of solar radiation received directly from the sun. Second, diffuse radiation. Diffuse radiation is sunlight that has been scattered in all directions by molecules and particles in Earth's atmosphere before reaching the surface. It is a result of multiple scattering events. Diffuse radiation is less concentrated and appears to come from various directions in the sky rather than directly from the sun. It creates even illumination on overcast days and reduces the contrast of shadows. Diffuse radiation can be measured using pyranometers equipped with a shaded or secondary sensor that shields direct radiation, allowing only diffuse radiation to be recorded. Third, reflected radiation. Reflected radiation is a sunlight that strikes a surface and is reflected off that surface, redirecting solar energy in a different direction. It can occur when sunlight interacts with various objects such as buildings, water bodies or the earth's surface itself. Reflected radiation depends on the albedo or reflectivity of the surface it encounters. Surfaces with higher albedo values like snow and ice reflect more radiation, while darker surfaces like forest or asphalt absorbs more radiation. Examples of reflected radiation includes the glare from a shiny car surface, the reflection of sunlight off a lake or sunlight bouncing off a mirror. Understanding these three components of solar radiation is essential for various applications including solar energy system design, climate modeling and assessing the impact of radiation on the environment. It also helps in optimizing the use of solar energy resources and predicting the behavior of solar radiation under different atmospheric and surface conditions. Solar radiation is a radiant energy emitted by the sun comprising of ultraviolet, visible and infrared radiation. The amount of solar radiation that reaches any given location is dependent on several factors including the geographic location, time of day, season, landscape and local weather. Because the earth is round, the sun strikes the surface at different angles ranging from 0 degree just above the horizon to 90 degree directly overhead. When the sun rays are vertical, the earth's surface gets maximum energy possible. The more slanted the sun rays are, the longer they travel through the atmosphere, becoming more scattered and diffuse. Solar constant. Solar constant is a rate at which solar energy at all wavelengths is received per unit area at the top level of Earth's atmosphere. The solar constant is approximately 1368 watts per meter square, although it may vary slightly depending on solar activity and other factors. Solar constant is a fundamental constant used in solar energy calculations and atmospheric science. It serves as a reference point for measuring the energy output of the sun and helps in understanding the amount of solar energy that earth receives at a specific location. Solar insolation or solar irradiance. Solar insolation, often referred to as a solar irradiance, is the amount of solar electromagnetic radiation received on the surface of the earth or any other surface per unit area over a specified time period. It includes all forms of solar radiation such as direct, diffuse and reflected radiation. Solar insolation is typically measured in units of watt per meter square and is used to quantify the amount of solar energy available at a given location and time. Solar insolation varies throughout the day and year due to factors like sun's position in the sky, cloud cover and geographic location. It is highest when the sun is directly overhead and lowest during night time. Solar insolation is a crucial parameter in solar energy systems and applications, as it determines the amount of energy that can be harvested from solar panels or collected by solar thermal systems. Accurate knowledge of solar insolation helps in system design, energy production, estimation and optimizing the use of solar resources. In summary, the solar constant represents the constant intensity of solar radiation at the outer atmosphere of the earth, while solar insolation quantifies the actual amount of solar radiation received on the earth's surface, considering various factors affecting the radiation's intensity and availability. Both terms are essential for understanding and utilizing solar energy for various applications. Solar energy can be used through two different routes, namely solar thermal energy and solar electric energy, also called as solar photovoltaic. Solar thermal systems use the sun's heat and convert it into heat energy, while solar photovoltaic systems use sun's heat to produce electricity. First, we will discuss about solar thermal energy. Solar thermal energy. Solar collectors, often referred to as solar panels, are the primary component of solar energy systems that capture sunlight and convert it into thermal energy. These collectors come in various designs, including flat plate collectors and concentrating collectors. Concentrating collectors use mirrors or lenses to focus sunlight onto a smaller area, thus increasing the temperature of the collected heat. A heat transfer fluid such as water, oil or a specialized heat transfer fluid is circulated through the solar collectors. It absorbs the heat from the sunlight and carries it to a heat exchanger or storage system. In many solar thermal systems, a heat exchanger is used to transfer the collected thermal energy from the heat transfer fluid to a working fluid. This working fluid can be water or any other fluid with a lower boiling point. The heat exchange process converts the thermal energy into mechanical energy. In some solar thermal systems, the high temperature working fluid is used to produce mechanical energy through a heat engine such as a steam turbine or a Stirling engine. This mechanical energy can then drive an electricity generator to produce electricity. Solar thermal systems can be configured for either electricity generation or heat production. In concentrated solar power systems, the mechanical energy is used to drive a generator, producing electricity. CSP technologies include parabolic trough, solar tower and dish Stirling systems. Solar thermal systems can be used to produce heat for applications like space heating, water heating and industrial processes. Solar thermal energy has a wide range of applications and its versatility makes it a valuable renewable energy source for various sectors. Here are some common applications of solar thermal energy. Number 1, electricity generation, concentrated solar power, parabolic trough systems. Parabolic trough collectors focus sunlight onto a central receiver tube containing a heat transfer fluid. The heated fluid is then used to produce steam, which drives a turbine to generate electricity. Solar tower systems. Solar towers use an array of mirrors, helistostats, to concentrate sunlight on a central receiver at the top of a tower. The heat collected at the receiver is used to generate steam and drive a turbine for electricity production. Dish Stirling systems. Concentrating dish systems focus sunlight onto a small Stirling engine, which converts the thermal energy into mechanical power to generate electricity. Second, solar water heating system. A solar water heating system is a renewable energy technology designed to harness sunlight to heat water for domestic, commercial or industrial use. These systems use solar thermal collectors to capture solar energy and transfer it to a heat transfer fluid, typically water or special heat transfer fluid, which is then used to heat a water storage tank. Solar water heating systems are a cost effective and environmentally friendly way to provide hot water for various applications including bathing, space heating and industrial process. Here is how a typical solar water heating system works. What are the main components of solar water heating systems? Number 1, solar collectors. These are the key components of the system and comes into two main types. Flat plate collectors, number 1. These are the most common type and consist of an insulated box with a glass or plastic cover, a dark absorber plate usually made of metal and a series of tubes or channels through which the heat transfer fluid flows. Evacuated tube collectors. These collectors consist of multiple glass tubes, each containing an absorber tube where the heat transfer fluid flows. They are more efficient in colder climates and can maintain high temperatures. Second, heat transfer fluid. The heat transfer fluid circulates through the collector and absorbs heat from the sun. Common fluids include water or a glycol water mixture in colder climates to prevent freezing. Third, heat exchanger. The heat transfer fluid passes through a heat exchanger where it releases its heat to a separate loop of water that is used for the intended application such as domestic hot water or space heating. Solar controller. A controller regulates the operation of the system by monitoring the temperature of the collector and the temperature of the water in storage tank. When the collector temperature is higher than the tank temperature, the controller activates the circulation pump to transfer heat from the collector to the storage tank. Storage tank. A well insulated storage tank stores the heated water until it is needed. The tank can be a standalone unit or integrated with an existing water heating systems. For example, a conventional electric or gas water heater. Now, the operation of solar water heating system. During daylight hours, solar collectors are exposed to sunlight. The absorber plates in the collectors absorb the solar energy and convert it into heat. This heat is transferred to the heat transfer fluid flowing through the collector's tube or channels. As the heat transfer fluid circulates through the collector, it gains heat from the absorber plate. This hot fluid is then pumped to the heat exchanger. The heat exchanger is located within or connected to the storage tank. It transfers the heat from the heat transfer fluid to the water inside the storage tank, thus raising the temperature of the water. The heated water is stored in the tank until it is needed. When hot water is required for showers or other purposes, it is drawn from the storage tank. If the water in the tank is not hot enough, a backup heating source, example an electric or gas element, may be used to ensure a continuous supply of hot water. There are broadly two ways of generating electrical energy from solar power: the thermal route and direct conversion route through photovoltaic. Further, there are two basic types of solar thermal power stations: power tower and parabolic trough collector. Power towers are also known as solar power towers, are a type of concentrating solar power technology used to generate electricity by harnessing sunlight. Power towers use a large array of sun tracking mirrors called heliostats to focus sunlight onto a central receiver located at the top of a tall tower. The intense concentration of sunlight at the receiver generates high temperatures, which are then used to produce steam and drive a power cycle to generate electricity. Here is how a typical power tower system works. Number 1. Heliostat field. A field of thousands of heliostats, typically flat mirrors, mounted on motorized tracking systems, surrounds the power tower. These heliostats track the sun throughout the day, adjusting their angles to direct sunlight towards the tower's receiver. The receiver is a specialized component located at the top of the tower. It is designed to withstand extremely high temperatures. The receiver absorbs the concentrated sunlight reflected by the heliostats and converts it into heat. A heat transfer fluid such as molten salt or air flows through the receiver. The intense heat from the concentrated sunlight heats the fluid to extremely high temperatures, often exceeding 1000 degrees Celsius. Many power tower systems incorporate thermal energy storage to store excess heat generated during sunny periods. The stored thermal energy can be used to continue electricity generation during cloudy days or at night, ensuring continuous power production. In some power tower systems, the high temperature heat transfer fluid is used to generate steam. The steam can be used directly to drive a steam turbine or be used in a heat exchanger to generate high pressure steam for electricity production. The steam generated by the system is used to drive a power cycle such as a steam turbine or a Brayton cycle engine. As the steam expands and flows through the turbine or engine, it generates mechanical energy which is then converted into electricity by a generator. Power towers are well suited for regions with high direct sunlight and can contribute to sustainable and environmentally responsible energy future. There are one of the several CSP technologies used to harness the sun's energy for electricity generation. A parabolic trough collector is a type of solar thermal collector used to concentrate sunlight and capture it as heat. It is one of the most common and mature technologies in the field of concentrating solar power and is widely used in large scale solar thermal power plants. Parabolic trough collectors are known for their distinctive parabolic shape, which allows them to concentrate sunlight onto a linear receiver tube running along the trough's focal line. Here is how a parabolic trough collector works. The main component of a parabolic trough collector is the parabolic shaped reflector. This reflector consists of a long, curved and reflective surface that concentrates sunlight along its focal line. The shape of the reflector is designed to ensure that the incoming sunlight is focused precisely onto the receiver tube. A receiver tube is positioned along the focal line of the parabolic trough. This tube contains a heat transfer fluid, typically synthetic oil or molten salt, which flows through it. The concentrated sunlight is directed onto the receiver tube, heating the fluid within. The reflector and receiver tube are mounted on a support structure that allows the parabolic trough to track the sun's movement throughout the day. This ensures that the sunlight remains focused on the receiver at all times, maximizing energy capture. Operation of a parabolic trough collector. As the sun moves across the sky, the parabolic trough follows its path by tilting and rotating to keep the sunlight focused on the receiver tube. This precise tracking is essential for optimizing energy capture. The concentrated sunlight strikes the receiver tube, heating the heat transfer fluid inside. The heat transfer fluid absorbs the energy and becomes extremely hot, often reaching temperatures of several hundred degrees Celsius. Depending on the specific application, the heated fluid can be used for various purposes. In some systems, the hot fluid is sent to a thermal energy storage systems where the heat is stored for later use. In others, the heated fluid is used to generate high pressure steam, which can be used to drive a steam turbine to produce electricity. Parabolic trough collectors are known for their high efficiency in concentrating sunlight and are widely used in large scale concentrating solar power plants. They have been a key technology in the development of solar thermal energy for electricity applications and industrial applications. Direct conversion of solar energy to electricity takes place through photoelectric effect. The photoelectric or solar photovoltaic effect is a process in which the two dissimilar materials in close contact produce an electrical voltage when struck by light or radiant energy. Discrete packets of light energy known as photons strike the photovoltaic cell, knocking the electrons in the silicon material out of their normal energy state, putting them in a position to conducted as electricity. Now, what are the components of a solar photovoltaic system? A solar photovoltaic system consists of various components that work together to generate electricity from sunlight. A typical solar PV system consists of number 1, solar PV modules. Solar PV modules, also known as solar panels, are the primary components of a solar photovoltaic system. Each module contains multiple solar cells made of semiconductor materials, usually crystalline silicon or thin film materials. These cells are where the photovoltaic effect occurs. Inverter. The electricity generated by solar panels is in direct current form. However, most of our electrical appliances and the grid itself operate on alternating current. The inverter is a crucial component that converts the DC electricity produced by the solar panels into AC electricity, making it compatible with household and grid systems. Mounting structure. Solar panels need to be securely mounted in a way that optimizes their exposure to sunlight. Mounting structures can be fixed, tilted or tracking systems that adjust the angle of the panels to follow the sun's path throughout the day. Solar charge controllers for battery based systems. In off-grid or hybrid solar photovoltaic systems with battery storage, a solar charge controller is used to regulate the charging and discharging of batteries. It ensures that batteries are charged safely and efficiently. Batteries for off-grid and hybrid systems. In off-grid or hybrid solar photovoltaic systems, batteries are used to store excess electricity generated during the day for use during periods of low or no sunlight, such as at the night or during cloudy days. Each component of a solar photovoltaic system plays a crucial role in the generation, conversion and distribution of electricity from sunlight. The specific components and systems design can vary based on the type of photovoltaic system, grid tied, off grid or hybrid, and the individual requirements of the installation. Now, how solar photovoltaic technology works? Solar panels are positioned to capture sunlight. When sunlight strikes the solar cells within the panels, it transfers its energy to electrons in the semiconductor material. The energy from the photons in sunlight excites electrons in the semiconductor material, causing them to move within the cells. The movement of these excited electrons creates an electric current, generating direct current electricity within the solar panels. The DC electricity generated by the solar panels is sent to the inverter, where it is converted into alternating electricity. This AC electricity can be used to power electrical appliances and devices in homes, businesses or fed into the electrical grid. With this, we will end our today's lecture here. Thank you for your patience and we will meet in the next lecture. Thank you.